Hi all, today I will continue with the previous topics that we have already talked about, which is about the internal force. Okay, but before, I have to let you know what is the basic behind internal force. Whenever we know failure in a structure, okay, actually it is caused by the stress which is happening at that particular structure is exceeding the strength of the structure. Maybe for some of you it will be a bit confusing, but you will learn about this next semesters in mechanics of materials, and you can find a lot of video in YouTube's about structural failure. Okay, this is some of the example. Okay, and the theory behind that. Okay, for example, try to imagine if you have a ruler and you give a bending load to that particular ruler. So this is, for example, a ruler. Okay, and you give a bending load, a moment, something like this. Okay, when the moment is still not that huge, okay, the ruler will bend, and it will bend like this. Okay, and until one particular point where the ruler can't hold it anymore, and it will break like that. Okay, the breaking point means that the stress which is happening at that particular point is higher than the strength of the ruler. Okay, the strength and the stress the stress of the ruler is directly proportional to the internal force and internal moment which is happening at the ruler internally. Okay, so that's why it is important for us to understand about internal force. Okay, the other example, if you pull the same rollers, okay, if we have the same roller and we pull it, okay, in the middle of the ruler, if I imaginary cut it in the middle, okay, we have the internal force, which is directly proportional to the stress which is happening of the ruler, at the ruler. So something like this. If I cut it like this, and then we have this, the free body diagram now become like this. I draw the thickness of the ruler now. Okay. I'm sorry for my drawing. Yeah, I know it's a little bit bad. Okay, and I pull it here and here. Later, this is what really happening there. There will be a stress at the cutting, at this particular cut. The stress there is proportional to the force F here divided by the cross-sectional area. Okay, And this is what you will learn, one of the things that you will learn in mechanics of materials. Okay. For this particular class, what we will learn is not the stress which is caused by this kind of load, but we want to know what is the internal force effect which is happening at a particular structure when a particular load is given to that particular structure. So if we want to find the internal force, for example, okay, and for this particular case, and we want to find the internal force at this particular section, okay, at this particular section, this is what we can do. Okay, we can cut that particular structure at the section that you want. For example, it's something like this. Okay, then you can analyze either the left cut or the right cut of the structure. Okay, this is the right cut. And this is the left cut. Okay. First, I want to analyze the right cut first. Okay, and we can see there that the external force which is given to this particular cut is like this, F. Okay, and like it or not, whenever we talk about statics, the equilibrium is supposed to be there. That's why we have to find something here at this side which is makes the this particular cut in equilibrium condition. That's why we can draw the cut like this. Okay, this is F there, and there's supposed to be another F here, which is the internal force which is happening at that particular cut. Okay, the same thing for the left cut. Okay, if I want to draw it, it's something like this. Okay, and there is a force to the left, external force to the left. Then we have to find the force which is happening at this side, internal force which is happening at this side, in order to make everything is in equilibrium. And in that case, what should we have here? It's supposed to be another force to the right, and this is actually the internal force of this particular cut. Okay, that's the easiest example of the internal force. Okay, and this is another example. At this particular structure, what we want to find is the internal force and the internal moment which is happening at L per 4 from A. So it's supposed to be around here. Okay, the same as before. We can answer this by creating a cut like this. Okay, and we can analyze either this part or this part. Okay, for the first example, I want to try to analyze the right part. Okay, for the right part, it's supposed to be like like this. We have to draw the free body diagram, of course. There is P on the right hand, and then I'm sorry, and SP as well around here, P. Okay, and we have to find all the reaction force and all the reaction moment at this particular location. Okay, then I first assume that the internal shear force is going up here, phi, and the internal moment is like that. Okay, and we have to find the value of the internal shear force and the internal moment. And I forgot about something. Before that, you have to know the sign convention first. Okay, whenever we have a cut like this, okay, the sign convention for positive shear force is like this, turning the structure clockwise, and the positive moment is like this. Okay, now we return back to the case here. How can we find the value of phi and the value of m there? As usual, whenever we have a free body diagram, we can have three equations to solve the problem. The first one is sigma fy equal to 0. Second one is sigma fx equal to 0. And the last one is sigma moment equal to 0. But unfortunately for us, for this particular case, there is no horizontal force. That's why we will not be able to use this particular equation. That's why we only have two equations here. But fortunately for us, the unknowns are only two. The first one is phi, the second one is m. Okay, now let's try to find the value of phi using sigma fy equal to 0. Using sigma fy equal to 0, what we have here is phi minus p minus p supposed to be equal to 0. In this case, what we get is phi is equal to 2p. Okay, and now using sigma moment at this particular location, okay, equal to 0, what we have there will be this distance supposed to be L per 4, this distance supposed to be L per 2. Okay, in that case, then we have moment m, m plus why keep doing it like this? I'm so sorry. Okay, m plus p multiplied by L per 4 plus p multiplied by L 3L per 4, because L per 2 plus L per 4 is supposed to be 3L per 4. Okay, and it's supposed to be equal to 0. Then we can find that M here is supposed to be same as, what is the value? Supposed to be minus P multiplied by L. So this is our internal moment at this particular location, and this is our internal shear force at this particular location. And we can try to solve the same problem but using the other part, the left part. Okay, this one. But in order to solve that, of course, we have to know all the external forces which is happening at point A first. Okay, that's why in order to do that, we have to solve this, the whole free body diagram. Once again, I'm so sorry about my drawing. As usual, it is not that good. Okay, and I assume we have AY here. What else? We have MA here, and we have AX here. Okay, as usual, we have 3 equations to solve all of these 3 unknowns. Okay, using a sigma fx equal to 0, what we will get is AX is equal to 0. Then, using a sigma fy equal to 0, what we will get is AY minus P is equal to 0, and AY is equal to 2P. And using sigma moment at A equal to 0, what we will get is MA plus PL per 2 plus PL is equal to 0, which means MA supposed to be minus 3 PL per 2. Okay. Minus here means that the direction is supposed to be the opposites of what I already draw here. AY here, the value is positive, which means that the direction is supposed to be the same as the direction of AY that I draw here. Okay, so now let's try to solve it. Solve the left part. Okay, then I will redraw the cut here. Just now what we have is the moment is 3PL per 2, and the shear force is 2P, if I'm not mistaken. Yep, correct, it's 2P. Okay, now we have to find the internal force which is happening at this particular point. and that particular interval supposed to make this particular free body diagram in equilibrium condition. Okay, now I assume that it has internal force, shear force of V going down, sorry, and moment like this. Okay, why I assume this way? Because just now we determine just now I tell you guys that the positive signs is like this. On the left cut, on the left of the at this side, okay, if we cut it on the left of a particular structure, phi is positive going up and moment is positive like this. And if we take a look at this particular cut and the force, the shear force happening there, we assume it positive if it's going down like this, and the moment is positive when the direction is counterclockwise. Okay. I want to check again. Yep, this is correct. As you can see here, this is the sign convention, which is you can find in the Merriam book. So whenever we analyze the internal force or the internal moment on the right side of a particular cut, okay, something like this, on the right side of a particular cut, the positive moment is counterclockwise and the positive shear force is going down. Okay, and if we analyze the left side of a particular cut, something like this is the cut, okay, and we analyze the left side of that particular cut, okay, the shear force positive is going up and the moment is clockwise. Okay, now let's return back to the previous problem example. Okay, that's why I assume it this way, is because this is the positive direction. So V going down is positive direction on the right side of a particular cut, and moment counterclockwise is the positive direction at the right side of a particular cut. Okay, now let's try to find the value of V and the value of M. Okay, using sigma Fy equal to 0, what we will have there is 2p minus V is equal to 0. Okay, and V is supposed to be equal to 2p. Okay, I want to recheck with the previous calculation that we have done on the right part. Okay, as you can see previously, we already analyzed the right part, this one, okay, and this is our calculation for phi at the same card. Phi there is supposed to be the same as 2p, and the exact value we found it here. So either you use the left part or either you use the right part, the value of the internal force and the internal moment is supposed to be exactly the same. And now let's try to analyze the value of m. Okay, sigma moment at the A, point A, equal to 0. Okay, and what we will have there is, if I assume that counterclockwise is positive, 3pl per 2, okay, plus m minus plus m, because m is counterclockwise, 3pl per 2 is counterclockwise as well, and the moment due to phi, it will be clockwise, that's why it's minus. So phi multiplied by L per 4. Okay, the length of this is supposed to be L per 4. And phi just now is 2p. So 2p multiplied by L per 4 equal to 0. This is supposed to be half PL. This one is 3PL per 2. So what we will have is M is equal to minus PL. Okay, let's check again. Our previous calculation said that the moment here is minus PL. So exactly the same. As I told you before, either the left part or the right part is supposed to be giving you the same value of internal shear force and internal moment. Okay. Now let's try to the last example. Last week I believe that you all already learned about the distributed force. Now I want to combine the internal force and the distributed force. So this is one of the problem like that. Okay, and the question here is, you are asked to find the internal force and internal moment at L per 2, which means here, in the middle, exactly in the middle. Okay, unfortunately for you guys, for my class, okay, the homework for you is the internal force and moment at L per 4 from the left pin support. Okay, so the one that I discussed here is slightly different. Okay, the same as before. You can analyze either the left part, okay, either the left part or the right part. Okay, but here the left and the right part, both of those, in order to solve this, we have to solve for the external reaction force first. That's why in this case, like it or not, we have to draw the whole free body diagram. This is W. Okay, at the left edge, what we will have is, I assume the name is A, AY, and AX. Then on the right edge, we have PY here. for the external reaction force at the pin and the roller. Okay. Now let's try to review again what we learned last week. Okay. If we have this kind of distributed load, we have to find the centroid in order to get the external reaction force. Okay, and because the W is constant, the centroid will be exactly in the middle. Okay, so in this case, we can replace the W with, because the length is L, with WL exactly in the middle in order to find the external reaction force. Okay. As usual, if we have a free body diagram, we will have three equations to solve all of the unknowns, and in this case we have three unknowns as well. So so it fit well. So sigma fx equal to 0 in this case, because nothing there except for ax. In this case, ax will be 0. Then sigma fy equal to 0. What we will have here is ay plus by minus wl is supposed to be equal to 0. Then sigma moment at A is equal to 0. In this case, what will I get is WL multiplied by L per 2 minus By multiplied by L is supposed to be 0. Okay, in this case, we will be able to find By. By is supposed to be WL per 2. Then substitute this value here, WL per 2. What we will get is AY is equal to WL per 2 as well. Now we got all the external reaction forces that we need. Okay, so the so now we can try to calculate for the internal force at L per 2. Okay, this is one important thing that I need to tell you guys. In order to find the external force, like this, external reaction force, By, Ay, and Ax, you can assume that W is represented by the whole W. Okay, the whole W is represented by this concentrated force, WL, exactly at the centroid. But if you want to find the internal force, okay, you can't use the same like this. Okay, so in order for us to find the internal force, we have to draw the free body diagram of that, either the left section, the left part, or the right part. So in this case, we will cut it here, exactly in the middle. at where we want to find the internal force and internal moment. Okay, and then we will draw the left or the right free body diagram. In this case, it will be exactly the same. Okay, and let's try the left. We will only try once here, only the left one. Okay, so this is the left free body diagram. What we will have here is there will be W. The length here will be L per 2. What else? The reaction force, what we will have is AY equal to WL per 2. Okay, as usual, I will assume the direction of the internal shear force and the direction of the internal moment positive. So phi is going down here and moment is counterclockwise because at the right side of a particle cut, the positive phi is going down and the positive moment is counterclockwise, as I told you previously. Okay, now in order to solve this, okay, we can assume that this whole W, okay, can be represented by concentrated force at the centroid. But now, instead of L for the length, now the length is L per 2. So now, the free body diagram, I can draw it this way. This is the concentrated force exactly in the middle. I'm sorry, I think I draw it slightly to the left. Okay, but what I mean is exactly in the middle at L per 4. Okay, and the value is supposed to be WL per 2. And we have WL per 2 here as well. And phi and moment. Okay, and we can solve this by using sigma moment equal to 0 and sigma Fy equal to 0. Sigma Fx, I'm sorry, what happened here? How to read? Yeah, sigma Fx equal to 0. We can't use this because there is no horizontal forces there. Okay, let's use the new page. Let's draw again. WL per 2. And WL per 2 here. Phi M per 2. Okay, now using sigma Fy equal to 0, what we will get is WL per 2 minus WL per 2 minus phi equal to 0. Okay, in this case, the value of phi is 0. Then, using sigma moment equal to 0, at A, what will I get is from this WL per 2 multiplied by L per 4 clockwise positive, okay, minus M equal to 0. V is not there because V is equal to 0. That's why what we will get is M equal to WL square by 8. That's it. And actually that's all for this particular session. For the next session, I will continue with how to handle the internal force whenever we want to find internal force and internal moment at more than one particular point or location. For today, we have only concentrated on handling a problem where we want to find the internal force and internal moment at one particular point or location. Okay, that's all for this session. See you.